whether the two groups differ in the mean number of pictures that are printed. So we have 8 digital camera owners and 8 standard cameras. Okay, and we ask them how many pictures they printed in the past month. So let's take a look. So what we're trying to test here is whether mu digital is different from mu standard. Okay, and that would be our alternative hypothesis. Agree? Because there's no equal sign in it. And so the null hypothesis is going to be the one with equal sign. All right, and this is our step one. And then again, because we are testing the two means, the only test that is available here is the t-test, right? And in the t-test here, we are interested in the average, the sample average difference, and then we divide this by the pooled variance, and then get the number based on this formula, right? Again, before we can get to this point, there's quite a number of calculations, right? The average, the variances, and then finally the pooled variance. So let's go through this again. So it's digital average. You take the first group of data, 15, 12, up to 19. You divide this by 8, and you have 18.25. And then another group, the standard one, you have 0, then 24, then all the way to the last one. And here we have 16.5. For the variances, okay, it's the same as before. Okay, you use this formula again. So here I will have 15 square, 12 square plus total dot to 19 square minus 8, and then square of first average, and then divide this by 8 minus 1. And this one you have 42.21429. So similar for the second group. We have 0 square plus 24 square plus total dot to the last one. Again, we have 8 data points in this group, and then the average is 16.5, and then we square it. Again, we divide this by 8 minus 1, and for this case, we have 367.7143, quite large, right? Yeah, so you will almost believe yourself to make an incorrect calculation, but if you look at the data, you don't have to worry too much because you have many zero appear and you have some large value, and in fact this is a correct calculation. So now at the end of this stage we can calculate the pooled variance. Alright, so you fill in the numbers carefully one by one. Okay, make sure you leave enough decimal places in the middle of the calculation to avoid too much round of error. Alright, so the answer is 204.964. So that is the pooled variance. Now with all this ready, we can do our calculation. So x bar d would be 18.25, okay, 16.5 the second group, multiply by 0, and down here we will take the pooled variance, and then multiply 1 over 8 plus another 1 over 8, then your test statistic is 0.2444719. Now then you can move forward to state your rejection region. And looking at the alternative hypothesis, this tells you that you have a two-tailed test, and so you are going to have two parts in your rejection region. Now let's state this. Rejection region. So one is t less than minus of t alpha, okay, which is, if we go back here, okay, that would be 5%. So here we say 5% over 2 because it's a two-tailed test. And for the degrees of freedom is NB plus NS minus 2. Alright, so that is minus T 2.5%, 14. Alright, and we go to the table, you look at this column, and go to the row 14, and you can see the critical value is minus 2.1449. And this is only one part. The other part is t greater than t 2.5%, 14. Alright? And that is again the same value but positive one. Now you have your rejection region, you have your test statistic. Now you can state your conclusion. So here is your rejection region, 2.144 something, and minus 2.144 something. Okay. And your test statistics is somewhere here, 0.2444 something, right? So your conclusion is do not reject. Agree? Do not reject the null hypothesis, and don't forget that alpha equals to 5. Alright? Now you may ask, what about the p-value method? Okay, we said in the lecture notes, right? When we discussed the lecture materials, p-value is possible, but due to the limitation of the t-value, we won't require you to do that. Alright, so whenever you are doing t-value, you don't have to worry about the p-value method. Alright, so this is this question. Now let's move on to another exercise. Exercise 5.2. Okay, so in this exercise, we are focusing on doing hypothesis test about the variance or variances. Okay, and the first one you will do, and I should say one of them is to test about one variance, and the other one will be test about two variances. Okay? So now let's look at this. Okay? Yeah, in terms of the variation, this kind of hypothesis test is very straightforward. Okay? There are not much variation in it. Once you see you are testing one variance, there will be only one way to go. All right. So now let's take a look of this example. Here we have a random sample of 100 observations from a normal population, and the variance was calculated to be 220. Now you may ask, is it possible to have population variance? It's possible, but there will be no point of doing any hypothesis test about it, right? If you have the population variance, why do you want to do a hypothesis test? Agree? So all the time when you have question like this, you won't be provided the population variance. Okay. Now here we want to see whether the variance is different from 300. Difference from 300. So this is going to be your alternative hypothesis. And so your null hypothesis is variance equal to 300. And this will be a two-tailed test because in the alternative you can see not equal. Now then next, in step 2, you have chi-square. This is only one formula to go, right? This is square. Then you fill in the value accordingly. Okay. So here, what do we put? Population variance. Okay, you may say, well, just now I said there will be no population variance provided, but now I need a population variance. Why? Yeah. This is based on the idea of hypothesis testing. Remember, we are asking about what if. Okay, so we are asking what if the null hypothesis is true. So if the null hypothesis is true, then the variance is what? According to this, will be 300, right? So we will put down 300 here. Okay, so here is 72.6. And then now it comes to the rejection region. This is not equal in the alternative, so there will be two sides. The difference from t-test, we don't put negative here, okay? Because the chi-square distribution is always on the positive side. So instead, we are looking at this. So typically, a chi-square value look like this. And we divide this up in two parts. Here, we are doing alpha equals to 5%. So on this side, you have 2.5%, 2.5% here. And this particular point, we name it as chi-square, 2.5%, and then degrees of freedom, 100 minus 1. Why 100? Because our sample size is 100. And for this point, this is chi-square, and then here we will look at the right tail area, which is here, right? So that means this is 1 minus 2.5%. And again, degrees of freedom is 100 minus 1. Alright, so the rejection region correspond to here, right? Whenever your test statistics appear in the yellow region, you reject the null hypothesis. So now let's write down the rejection region. Okay, and the other one, chi-square, bigger than chi-square, 2.5%, 100 minus 1. Okay, or if you prefer the natural notes notation, here I will write 5% over 2. Now, we can go to the table and check the value. So first, we know we should focus on this column. 2.5% column and 97.5 column. Okay, and then we will scroll down until we reach degrees of freedom 99. All right, so let's go down until we see it. Now we don't see exactly 99. Okay, and so we will just pick the one which is closest to it. That will be 100 in this case. So the degrees of freedom we're going to use is 100, even though the most correct value is 99. And we will get this 2, which is our critical value. Okay, let's go back to this. Okay, we see that this equals to 74.2219, and this one equals to 129.5612. Right, so now let's see if our test statistics fall into it. Yes, certainly, right? In this case, it will be somewhere here because this point is 74 point something, right? So now our statistics is in it, and so in our conclusion, we will say reject the null hypothesis. In other words, we have the reason to believe that the variance is not 300. All right. So this is how we do this test. Let's move on to question 6. Here you have a statistics professor who computes the variance mark of a final exam and find it to be 250. And now to somehow make the change in marking the final exam and wonder the result would whether the variance would reduce the wonder whether this would change the variance. Okay, that means the less variation. And here he obtained some sample of the data, and altogether there are how many? So here we collect 10 data points, right? And she wants to use 10% of dipole significance to test whether the variance has reduced. So what we try to do here is to see whether the variance is decreased, right? By decreasing, we mean it is less than what we had before, which is 250. So since this statement does not involve an equal sign, right? So this has to be the alternative hypothesis. And so the null hypothesis is sigma square greater than or equal to 250. And this is our step 1. And what is the next step? Sorry. So our next step is to calculate the test statistic. And again, it is s squared n minus 1 over sigma squared. All right. But here the sample variance is not immediately available, so we need to calculate it by ourselves. Now let's get x bar, because the variance depends on the average here. So let's get the average, which is 70 plus 92 plus dot 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 up to 60, and we divide this by the sample size 10, and we get 74. And next we have the sample variance. Again, we make use of this formula. So 57 square plus dot 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 up to 60 square minus sample size times the square of the average. And we divide this by 10 minus 1. And this gives us 210.2222. So with this, we can get our test statistic. First, we put down the sample variance, and then 10 minus 1. And then down here, population variance. Remember, we are asking, what if this is true? So we imagine this is equal. So what if this is greater than 250? So we ask, what if this is 250? And it turns out this statistics is 7.569. And now we can put down our rejection region, which is chi-square less than chi-square. Because here we see this is less than, so the things will be on the left side. And specifically, the rejection region we are looking at is like this. Since we move everything on one side, so we have all the 10% appear here. So all the rest are 90%. And so this point is chi-square, 90%, or we can say 0.9 degrees of freedom, 10 minus 1. All right. So whenever your test statistics appear here, you reject your null hypothesis. Now, what is that value? 90%. So here you will go to 90%, which is this column, and then degrees of freedom 9, right? So that will be this row. So it turns out that the value is 4.1682. Now remember, you don't put the negative sign. But this one is 4.1682. Now, is our test statistics in it? Look at this. It's somewhere here, right? So it's not in the rejection region. So in our conclusion, we will say do not reject the null hypothesis at alpha equals to 10%. All right, so this is another example about a test of one variance. Let's move on to the next one. Here we will change the question of another type. Here we want to test about two population variances. Here we have a computer anxiety rating scale. And this is a measure about an individual's level of computer anxiety. It ranges from 20 to 100. And here, a researcher from Miami University conducted an experiment about this anxiety, and it collected data from 172 students. So we want to see whether the anxiety experienced by the female and male are the same. So specifically, we want to see whether there's an evidence of the difference in the variability of the computer set anxiety experienced by male and females. Okay, so here we have our step one, sigma square male different from sigma square female. Right. Since it does not involve the equal sign, here we have the alternative hypothesis. And so the null hypothesis is going to be this. And this is our step one. Now step two, we need to get our statistic. And here we will use f-test. And there's a tricky part about f-test, okay? Again, this is due to the limitation of the table we have. When we do this, okay, whether you have equal, not equal, greater than, okay, you need to make sure that your f statistics calculated is greater than 1. And then you can focus on one side of the rejection region. All right, so keep this in mind. Okay, you have to make sure the f statistics is greater than 1. Okay, for whatever value you calculate. Okay, for whatever test you are doing. Okay, for variances, you have to make sure that your f statistics is greater than 1. So how do we know where we should how we should define it? Now there are two possible situations. One is you have your male variance divided by female variance, or you can do female variance divided by male variance, right? So which one should we do here? For this, you look at the standard deviation. Okay, you will put the one which is larger at the top. So that means in this case you will use this version, all right, instead of this, because this will ensure the f statistics is greater than 1, all right? Now let's put this over here, and now we can say we will be doing this. So this is the standard deviation. So before we use it, we have to square it. So same as the one for female. And so with this, we get 2.008449, right? And this is our test statistic. Here, next step is to get the critical value and then define the rejection region. So the rejection region, if you're looking at the not equal sign, it means here we're going to look at two sides. Now F distribution and chi-square look similar. Okay, they are also on positive side, and here we are doing 5% natural significance, so this is 2.5%, and the other side is 2.5% as well. And how do we define this point? It is quite similar to chi-square statistic. Okay? This is F, and then we will specify the right tail area, which is 1 minus 2.5%. And next, you need to look at 2 degrees of freedom. Okay? One is n m minus 1, and another is n f minus 1. And you have to be careful which one you should start with. To to find out which one you should start with, you look at your test statistic. If the one in the numerator is n, then the first one will be n, right? So similarly for the denominator, the one in the denominator determine the degrees of freedom of the second. Okay? So in this case, we have 100 males and 72 female. So this point is 99, and this one is 71. All right. Similarly for the other point, this is again F, and then this time just 2.5%, and then 99, 71. All right. So now you can specify the region. You write F greater than F 2.5%, 99, 71, and another one, right? To the boundary here. F less than 1 minus 2.5%, and then 99, 71. Okay, this is the rejection region. Now, here we will only have to check this value, right? Why? Because the way we organize our F statistic, here we always make sure this is greater than 1. So if this actually happens to reject the null hypothesis, it will always be appear on the right side. So even though this is the rejection region, but all we need to check is this value. Okay. Now, how do we check the value? Okay, you can go to the table, and you have to pay attention to the heading, right? Here we are doing a 2.5%, so you have to make sure you are going to a table with A equals to 2.5%. There are some other table with 1% and 5%, so you need to make sure you are in the correct page. Then next, you will identify the degrees of freedom. Okay, for the column, it tells us about the degrees of freedom in the numerator, okay, as is set here. And the first one is 99. All right, so we will go to find 99, and 99 is not here, and we pick the closest one, which is 100. Okay, and next, we will go to find the second degrees of freedom, which is 71. So again, we scroll down until we see 71, and here we don't have 71. Instead, we have 70. So we pick the one which is closest, which is 70. Then we can see the critical value is 1.5581. So this is 1.5581. So it's our statistics fall in the rejection region? Certainly, yes, right? Here, it appears here, since this point is 1.5581. All right? So finally, we can have our conclusion saying that we reject the null hypothesis that alpha equals to 2.5%. All right? So this is the this question, okay? Question 4 from exercise 5.2. And let's look at another one. Uh, so maybe we have a break, okay? Because we already have an hour doing this. Okay, so let's have 5 minutes break, and we go on and finish the rest of the exercise from chapter 5. Okay. Okay, let's continue with the exercises from chapter 5. And here we are doing exercise questions from exercise 5.2. Now here we have again two groups of data. Um, this is the uh, um, sorry here, right? This is the amount of food in a can. Okay, so this is a pet food. So the operations manager believe that the variability of cans filled in 9A is greater than 9B, okay? And you want to see where there's an evidence in it. So let's first state the statement we want to test. Here we want to see if variation from line A is greater than variation from line B. So is this going to be a null or alternative? That's right. There's no equal sign, right? So we will say this is alternative hypothesis. So we will know the null hypothesis is less than. Okay, and this is our step number 1. Now then in step number 2, here we have our test statistic. Okay, so for this one, again we have two versions, right? SA square over SB square, and then SB square over SA square. So which one should we choose? And for this one, because this is a one-tail test, we want to put everything on the right side. Okay, remember the F table we got is only those with the right tail area. Okay, about 2.5%. So we have to make sure the test statistics is something greater than something. Okay, greater, right? We have to make sure that we only check the uh, rejection region which is on the right side. So what it means is we we have to think of this. So now, when you look at the alternative hypothesis, there are two possible outcomes. You can have sigma square A over sigma square B greater than 1, or you put this on the other side, right? Sigma square B over sigma square A, but then that will be less than 1. Agree? Yeah, but we only want our rejection region on the right side, so we have to choose this version. Okay, in other words, your test statistics is going to be this one. All right. So please let me know if this somehow gets you confused. Okay, this is a very important point when you do F test about the variances. So now we know that at this point we will not be using this. Okay, instead we will do this one. So in step 2, we have SA square over SB square, and SA we have the standard deviation, so we need to take a square and divide this by square of another value, and I have 5.76. All right, and then we have our step 3, which is the rejection region. And because the way we put our alternative, right, we are doing this one, right? So our rejection region is going to be F greater than the critical value. Okay, here we are doing 5%, and this is one tail test, so there's no need to divide the alpha by 2. And then the degrees of freedom, you need to take note of your test statistics, A in the numerator. So the first one is 11 minus 1. The second is the one in the denominator, right, which is 16 minus 1. All right, then you can go to the table and check. And so this is the table. Again, you need to take care of the alpha you have. Here we are doing 5%, so we should pick the F distribution table with A equals to 5%. And then the first one is degrees of freedom 10, so we look at this column. Second degrees of freedom is 15, so we will look at this row. So this gives us the critical value 2.5437. All right, so we are almost done. Now, then next, you check whether your test statistic fall into the rejection region. Now here is our rejection region, and our test statistic is 5.76. So it certainly appear in the rejection region, right? So yeah, maybe just this, okay? This 5.76, our M statistic. Okay? Now we can state our conclusion. Reject the null hypothesis as alpha equals to 5%. Okay, so this is our conclusion, and that means we have evidence that the variance in line A is greater than that in line B. So the important point of this example is how you put down your test statistic, okay, to make sure you have greater, okay, in it. Then you can focus on the rejection region on one side. The next, question 6. So it's of similar question like before. Here we have a manager of dairy in, sorry, let me see. Okay, so again, it's about the food building a machine. We want to see whether a machine 1 is the average of machine 1 is different from, oh, sorry, not the average. Yeah, we want to see whether the two machines differ in their consistency of fields. Okay, and so the question they ask is, another question they ask is whether the pooled variance t-test is justified. Okay, so whether a pool variance t-test justified depends on whether they have equal variance, right? And how do we know whether they have equal variances? We can do a f-test to find out, right? So here, let's answer the first question. We want to see whether variability of machine 1 is similar to the one in machine 2. Okay, because it has the equal sign, is going to be our null hypothesis, and so your alternative is the opposite of it, and this is our step number 1. So how do we know which one we should use? It depends on whether we have the ratio greater than 1. So, but before we get to that part, we need the variance, right? So how do we get the variance? The variance is not directly given here, but we need to calculate it by ourselves. So we have two groups of data. So first, let's get the mean. The mean of the first group, 0.998 plus dot dot dot. So we're going to look at the first group. We add up all the data points and we divide that by their sample size, 10, which is 1.0002. Another group, which is from machine 2, 1.003 plus dot 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 up to 0.996. And be careful, we have one more data than the previous one. Here we have 11 data points. Here we have 1.000818. So this is our average. Next, we can get the variance. So for the first one, we again add up the numbers, but the square of this number subtracted by 10 times the square of the average, and then divide this by 10 minus 1, and we have 5.7333 times 10 to the power of minus 3. It's a very, sorry, 10 to the power of minus 5. Okay, it's a very small number. And then another group, 1.003 square plus dot 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 up to the last one in the group, 0.996 square minus 11 times the average, the square of the average, divided by 11 minus 1. And that gives us 1.13634 6364 times 10 to the power of minus 5. Oh, sorry, the first one should be minus 6. That's here. Okay, 10 to the power minus 6. So now at this point, you can tell which version you should use. To make the f statistics greater than 1, we have to put the second variance in the numerator because the second one is larger. All right. So in this case, we're going to take out this. So instead, we take this one. All right. So here, f s squared 1.136364 times 10 to the power minus 5 over 5.7333 times 10 to the power minus 6, and that is 1.98203. Okay, and now we have step number 3. Okay, we have the readjustment region. Okay, even though technically we should put down 2 parts, but only 1 part is needed, since we have made sure that our test statistics is greater than 1. So we have, because this is not equal, we have to divide this by 2, and then degrees of freedom 11 minus 1, okay, because the second group have 11 points. The second group, the first group have has 10, so this is 10 minus 1. So what you're going to check is to go to a table here. Let's enlarge it a little bit. You should go to the table with A equals to 2.5%, because what you are doing here is 2.5, and then you go for the column 10 because the first degrees of freedom is 10, and then second degree of freedom is 9. So you have the test statistic, which is 3.9639. Yeah, and the other part is f smaller than f1 minus 5% over 2, and then 10 and 9. Okay, but for this one you don't need to check, because if this happened to reject the null hypothesis, it will be always the one on the right side, because the way we organize our f statistic. Here we have our last step, our conclusion. Is this in the rejection region? It is. So what we have here is f distribution. Okay. This one is 3.9639. And we have another value, which is this one, but we don't have to worry about it. Okay, we just have to check whether this is greater than this particular point. So this 3 point, sorry, our test statistics is 1.98203, and it is not in the region, so we don't need to reject our null hypothesis. So here our conclusion is do not reject the null hypothesis at alpha equals to 5%. All right, so here this is just one more example about how to choose, how to do a test about two variances, and in particular you want to pay attention to the test statistics because it depends on the sample value. All right, now if you still got questions, please let me know. Okay, now I'll be very happy to answer your question here. Now let's move on to the next one. Okay, now here this is from exercise 5.3. Okay, so the last part of chapter 5. We have an ANOVA table. Okay, and this question asks us to fill in the A, B, and C. There are a few relationships you have to know about this table. Okay, yeah, but first of all, remember the purpose of getting the ANOVA table is to identify the F statistics. Okay, this F statistics allows you to test whether the means of several groups are equal. Okay, remember the purpose. But before we can find out this value, we want to fill in the ANOVA table so that we can systematically to find out this F value. Okay, and to get the F value, you need to we need to know the relationship in this in the terms appear here. So first of all, the sum of these two values. So I need to write down. Okay, the first one is the sum of these two values equals to the total SS here, and also for this one. Okay, so A plus B will be 19. And on the other hand, if you look across each row, this MS will be SS divided by DF. Okay, always. So which SS and which DF you should use depends on the row you're in. So for example, for this 25, that will be 25 over A. And for this 3.75, that is 60 over B. Right? And the last one, the last relationship you have to know is F, which is MST over MST. Right? So where's the MSE and MST? This is the MST, and this is the MSE. Right? So these are the relationship you have to know, and with this you can find out A, B, and C. Now, so if you want to know more detail about this table, you can go to this page in the lecture notes. Okay, it tells you the names, the exact relationship for all this cell. So you can see here, if you add up these two, you will have n minus 1. You add up these two, you have the last one, right? And also tells you about this is the ratio of the SS over the degrees of freedom. Okay. Now let's do this one here. Okay. So what is A? Yeah, A, if you know A is the degrees of freedom, okay, you know that here we have the MST divided by degrees of freedom. Okay, A here is, sorry, the other way. So MST equals to SST here divided by the degrees of freedom, right? A. So A is then SST divided by MST. Yeah, looking at the information available in the table, we have SST equals to 75 and MS equals to 25. So A is 3. Okay. Next is B. Okay, we know from the slide that SST plus SSE equals to SST. Okay, what I mean is the relationship in this column. So using the symbol here, it means A plus B equals to 19. And we already get the A, right, which is 3. So with one additional step, we know that B is 19 minus 3, which is 16. And finally, for C, okay, I think this one is the most straightforward. Okay. F is MST over MSE. In this case, F is the value of C, and MST is 25, right? And MSE is 3.75, so C is 6.6667. All right, so that's how we fill in an ANOVA table. Here is the last question I want to cover. Okay, there are several more exercises or question like this in 5.3, but I won't do many of them. I will just pick one of them here because the procedure are all the same. Okay, you just involve a lot of calculations. Okay, so all you need is to be patient and do it carefully. All right. So now let's look at this. We have the um, we have what? We have the amount of spend they receive in the emails, okay, of 3 groups of staff or person in the university. So professor, administrator, and students. So we want to see whether the amount of spend they receive on average are the same. So what that means is we want to know whether the average spend received by professor, mu p, is the same as those received by administrator, mu a, and the same as those received by students. So this involves the equal sign, okay, and it always be the null hypothesis. And be careful about the alternative. You need to say this is not or means equal. As we have already discussed in the lecture, right? So if you are still worried about this statement, please let me know. Okay, I can explain to you one more time. Here we have the data, and we know now the alpha is 2.5%. So our next step is to get the F statistic. Okay, but before that, we need to find out the SST, SSC, and many the values in the ANOVA table, right? And by ANOVA table, I mean this one here. Okay. So here, let's do this step by step. So first, we have MP. We have 5 data points, right? We have 5 data points. So same as the other group. Okay, they all have the same number of people, right? And so the total sample size will be the sum of this, which will be 15. Then we need to get the average of each group. Average of spend received by professors, 7 plus 4 plus dot 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 up to 18, and divided by 5, and on average is 6.4. By administrator, this is 5 plus 9 plus dot 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 up to 10. Again, divide this by 5, 10.4. The student, 12 plus 4, 15. Here we have 10.8. The next is the variance. Okay. Then we have 7 square plus 4 square plus dot 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 up to 18 square minus 5, 6.4 square, and then divide the whole thing by 5 minus 4, and that is 48.3. And then another group, sorry, this should be P, 5 square. This is from the administrator group. That is 10.4 square. 4 minus 5 minus 1, 16.3. And finally, for students, 12 square, plus up to 15 square minus 5. Right, so these are the variances, and we also need to calculate the grand mean, which is the mean of the entire data set. So the formula we have is this one. And then this one is 5 times 6.4 plus 5 times 10.4 plus 5 times 10.8 divides everything by 15. And we have 9.2. And finally, we can get to our SST. MP times SP, and then grand mean square. Okay. So since we have 3 groups, then we have 3 terms, okay, in addition. So all you need to do is just to do it systematically. Now each time we subtract by the grand total, 9.2. Then we substitute the mean one by one. Okay, 6.4, 10.4, 10.8. Okay, that gives us 58. Sorry, 59.2. Finally, SSE. This is a 5 minus 1. So when you make use of this data, 6.3, 16.3 plus, all right, and then the variance is 409.2. Not yet, okay, we are not to the F statistics yet. So then next you need to draw the ANOVA table. Okay, so here is the name, right? Or you can say the source. Okay, so all you need is just to take this table, right, and then fill in each column and rows. So here is the source. It's the treatment, error, and total. And this is the sum of square. Oh, forget with degrees of freedom, MS, and then finally the F statistic. Here, sorry, here you have first one, okay, 59.2, SSE down here, 409.2, so the total will be right. And degrees of freedom here is always k minus 1. K is number of groups, so here will be 3 minus 1, which is 2. And this is m minus k. So we have 15 data points. Minus k means 15 minus 3, and we have 12. Okay, so down here is the sum of these two numbers, which is m minus 1 or 14 here. Then next is the MS. All you need to do is to divide the SS by the degrees of freedom. So here is 59.2 divided by 2, so which is 2.29.6, and this one is similar. Okay. You divide 409.2 by 12. Okay. You don't need to do this for the total row. Okay. So finally, we have the F statistics, okay, which is the MST divided by MSE. In this case, we have 0.868035.2. All right. So now with all this hard work, okay, we have our test statistic. Okay, and this is our step number 2. Now next, we can specify our rejection region, which is always on one side. Remember, in ANOVA, okay, even though you have a lot of calculation, okay, for this one, you have no variation in the form of uh, question. Okay, if you are doing an ANOVA test, it will be always like this. Okay, the only variation you have is the number of groups and number of data points. Okay. So your rejection region here, no matter what you do, it will always be like this. Okay, F greater than F. Here we are doing a 2.5% level of significance. So this will be 2.5. And so you should go to the table with A equals to 2.5%. And degrees of freedom, you pick these two numbers, 2 and 12. Then you should be able to see 2 and 12. Then the value is 5.0955. So that means here is our rejection region. Okay, and our test statistics right now is this, so it will be somewhere here, I believe. So in your conclusion, our step 4 is to not reject the null hypothesis. Right? So that means we don't have enough evidence to say there are differences among the mean span is we receive. All right, so this is the ANOVA test. Okay, even though it involves a lot of works, but I think they are all straightforward, right? Once you remember the step of getting all this. Okay, so this is all the exercise I want to cover in chapter 5. And next week I will do a summary of what we have learned from the entire course, and then I will do exercises from chapter 6. All right. So if you got questions, please let me know. Okay. Anytime. Okay. You can let me know. Then we can make an appointment. We can meet on the Microsoft team, or you can simply do the discussion with me through email. All right. So I stop here. See you next week.